Hello, this podcast is part 2 in a two-part series on kinematic graphs and uniformly accelerated motion. In part 1, we learned how to determine velocity from a position time graph, acceleration from a velocity time graph, and displacement from a velocity time graph when we have uniform accelerated motion. In this part, we're going to learn how to create acceleration time graphs, and we're going to learn how to qualitatively analyze kinematic graphs and motion maps. Let's get started and see how we create acceleration versus time graphs from a velocity time graph.
We use a similar process as we used when we were creating a velocity time graph from a position time graph. When we had a position time graph, the slope of that graph gave us the velocities. Since the slope of the velocity time graph gives us the acceleration, the process is similar. First, we need to calculate the slope of each line segment on the velocity time graph. So we have 1, 2, 3, 4 line segments. So we're going to go ahead and calculate the slopes. For this first section, we have a rise of 60 meters per second, and we have a run of 10 seconds. So the rise divided by the run is going to give us a slope of 6 meters per second squared. If we come up here and look at the next line segment, we have a constant velocity, so we have no rise, and even though the run is 5 seconds, when we have no rise, the slope is going to be 0 meters per second squared. We move on to calculate the slope of this long segment. We have a rise. We go from 60 meters per second to negative 40 meters per second. So we have a rise of negative 100 meters per second over a run from 15 to 40. That's a run of 25 seconds. When we do that division, we get a slope of negative 4 meters per second squared. Finally, we want to calculate the slope of this last line segment. We go from negative 40 meters per second to 0 meters per second. We have a rise of 40, a positive 40 meters per second, and we have a run from 40 seconds to 55 seconds, so the run is 15. When we do 40 divided by 15, we wind up with a slope of 2.7 meters per second squared. Now we need to transfer these slopes, which are really acceleration, down to our acceleration versus time graph. So we're going to draw flat lines because, again, during this time interval from 0 to 10, the slope was the same. So that means our acceleration is constant, which means we're drawing a flat line at the appropriate values. So from 0 to 10 seconds, we draw our line at what would be 6 meters per second squared. For 10 to 15 seconds, we draw our line at the time axis, which represents an acceleration of 0 meters per second squared. In our next time interval, from 15 seconds to 40 seconds, we're going to draw the flat line at negative 4 meters per second squared. In our last interval, from 40 to 55 seconds, we're going to draw the line in the positive region at an acceleration of 2.7 meters per second squared. This is how you create an acceleration versus time graph from a velocity versus time graph. Let's move on to our last section of this podcast, and we're going to learn how to analyze kinematic graphs. Specifically, we're going to learn how to take one representation, in this case a position time graph, and create the velocity time graph, the acceleration time graph, and the motion map. In using this process, we'll be able to be given any one of these 4 representations and create the other 3. Here we have a motion that changes here where the dashed line is. Initially we have a curved position time graph, then it turns into a straight line. So we need to break this down into 2 different sections as delineated by the dashed line. Now sometimes you'll just have a single shape and you won't have to break the motion into 2 different halves. But I wanted to give us an example where we had a complex motion that changes at some point. First thing we need to do is look at this, and we notice that the curve starts with a flat slope of 0 and it gets steeper and steeper, and the object is moving in the positive direction. That tells us we're speeding up in the positive direction. Well, what does that tell us about our velocity line? It tells us that the velocity needs to get larger in the positive direction and that it needs to start at 0. So we're going to have a positive slope line that starts at 0. So we go ahead and draw that. We don't know exactly where to put this ending velocity because we don't have a scale here on our position time graph to give us a specific velocity, but we know it's going to be in the positive region. So you just start at 0, because that we do know, because this is starting at 0 slope. We start at 0 with a positive slope. Next, let's go to the second region, and we see that this straight line, of course, has constant velocity moving in the positive direction. Well, because the velocity is constant, we know that this line is going to be flat and in the positive region. And it's actually going to be at the same velocity that this segment ended with. So we're going to draw our flat line right here at the end of our positively sloped line. Now, to move on to the acceleration time graph, we need to look at the slope of our velocity lines, because remember, the slope of the velocity lines tells us the acceleration. So if we look at the slope of this line, we know that it's a constant slope and that it's in the positive region. That means that we are going to have a flat line in the positive region. So we go ahead and draw our flat line in the positive acceleration region. Now we need to go on and look at this section of the velocity timeline, and we see that the slope is 0 because it's a flat line. So the slope is 0. That means our acceleration is 0. So we're going to have a constant acceleration at 0. We draw the flat line on the time axis, which represents an acceleration of 0. Let's move on and take our acceleration time graph and create a motion map. We have an object speeding up in the positive direction for the first section, and then the second section we have it moving at constant velocity also in the positive direction. Notice on our position time graph, the position curve started at 0, so we need to start our dots at position 0. So I'm going to start putting in the dots. It's speeding up, so I'm showing these dots getting further apart because this is the speeding up phase. Now it turns into the constant velocity phase. The spacing between these two dots is the same as the spacing between these two dots. We also need to show acceleration. But remember, for acceleration, the dots are position dots, so we're just going to draw them in the same positions. Doesn't matter whether you're showing velocity vectors or acceleration vectors, the dots are always in the same spot for acceleration and velocity. Now we want to draw our velocity arrows. Initially, the arrows are going to be getting longer because the object is speeding up, and then we have our constant velocity where the arrows are staying the same length. Now we go ahead and do our acceleration arrows. They are constant, so in this first half the acceleration is constant. These arrows are going to be the same length. We get to the constant velocity section, and notice in this second section the acceleration is 0. That means we are going to have no arrows on our position dots, because while we still have velocity, we're still moving, we have no acceleration because we're moving at constant velocity. This is the process you use to start with one representation of motion and create the other 3 representations of motion. Following this process, you could be given the motion map and work your way through the position time graph, the velocity time graph, and the acceleration time graph.
Well, this wraps up part 2 in our 2-part series on kinematic graphs and uniform accelerated motion. I hope this helped, and have a good day.